Hello again. It's a great honor for me to introduce Professor Anne Greenbaum. Professor Greenbaum is in the Department of Applied Mathematics of the University of Washington. She got his PhD in the University of California, Berkeley, and is her Bachelor of Science in the University of Michigan. Formerly a research professor at the Courant Institute at New York University from 86 to 98. She got Science Fellow in 2015 for contribution to theoretical and numerical linear algebra, awarded the Bolzano Honorary Medal for merit in the mathematical science in 97, the SIAM Activity Group on Linear Algebra Award for outstanding paper in applied numeric and applicable linear algebra from 91 to 93. Her field of interest include applied linear algebra, numerical analysis, operation research, and scientific computing. Some of his research interests are non-normal matrices, numerical linear algebra, and iterative methods for solving large linear systems. She also works with integral equation and fast methods for solving the corresponding PDEs. She wrote some books. The first one, Iterative Methods for Solving Linear Systems. This book has about 2,000 citations in the Google Scholar. And again, her new book, Numerical Methods, is a very, very nice lecture. Now I am asking Professor Greenbaum to start her lecture. Please.
Great. Okay, well, I want to thank everyone for the excellent introductory talks to things like Crouzet's conjecture from Michael Overton, the numerical range from Chi-Kwang Lee, and Chebfun from Nick Trefethen. All of those are relevant to what I'm going to talk about today. I will talk about a little bit about Crouzet's conjecture. I'll also mention some associated problems like extremal Blaschka products and other K-spectral sets. And this is joint work with a number of people. Can you see my pointer, or do I need to do something? Oh, there it is. Okay, so this is joint work with all of the people listed here: Kelly Bickel, Michelle Crouzet, Pamela Gorkin, Kenan Lee, Thomas Ransford, Felix Scheninger, and Elias Begert. Okay. So there was a AIM workshop on Crouzet's conjecture in 2017. You'll notice a lot of the same people in that AIM workshop that we have here today, just so that you get to know the people. Whoops, the people. Why does this keep moving? Let's see if I can do this. I'm not so good at it. This is Michelle Crouzet. Palencia, you heard about, of the Palencia-Crouzet theorem with 1 plus the square root of 2. And of course, you've met a number of the others: Nick Trefethen and Michael Overton and Abbas Salami. Chi-Kwang is in here somewhere. There he is. These are my two of my students, Kenan Lee and Trevor Caldwell, who graduated recently. So we've done quite a bit of work on Crouzet's conjecture, and yeah, so just to remind you what the conjecture is, and by the way, please feel free to interrupt with questions in the chat bar. I can see the chat below me. So if you have questions along the way, please feel free, and I'll try to look at that occasionally and answer questions. All right, so let A be an n by n matrix. In 2004, Michelle Crouzet conjectured that for any polynomial or analytic function f, norm f of a is less than or equal to twice the maximum value of f on the numerical range. And this seems like a very basic result. If we think we understand functions of matrices and the numerical range, it seems like we should be able to either prove or disprove this. But that proof or disproof has remained elusive. There was a big breakthrough in 2017 when Cruzet and Palencia showed that they couldn't necessarily get 2, but they got the bound 1 plus the square root of 2, or about 2.415. The conjecture with 2 remains open. I highly recommend this paper by Cruzet and Palencia. It's a very easy to read paper, and it's short. It's all of 6 pages, so you can read it rather quickly. And I want to just summarize their method of proof because I think it's important and it's easy. Okay, so let's start with the Cauchy integral formula. F of a is 1 over 2 pi I times the integral over the boundary, the region of the resolvent times f. Let's translate that into an integral with respect to arc length and bring the 2 pi I inside so that we have, oh, this is, so that we have this kind of expression, okay? A new idea, or one that I certainly wouldn't have thought of, was also to look at the Cauchy transform of not just f, but of the complex conjugate of f. Okay, so that kind of erases things when I do that. I'll stop doing that. Okay, so yuck. At any rate, this was the integral of the same thing that we had up here, except that f had its, we took the complex conjugate. Okay, so the first thing to note is that if you form this matrix M that consists of this resolvent-like quantity together added with its Hermitian transpose, that matrix is positive semi-definite for all S if omega is a convex set containing the numerical range. The way they showed this was to show that on a tangent line to the numerical range, the smallest eigenvalue of this matrix is 0. On the side containing the numerical range, it's negative, and on the other side, it's positive. So that was the first piece of the proof. With that, they were able to show that norm f of a plus g of a star, remember g of a was the Cauchy transform of the complex conjugate of f, norm f of a plus g of a star was less than or equal to 2. And that's pretty easy to show. Just to sketch the proof, take any 2 unit vectors, u and v, look at u star f of a plus g of a star times v. That's the integral of u star times this matrix M times v times the function f. F is bounded by 1 in omega, so we just replace the absolute value of the integral by the integral of the absolute value. And now, using the fact that M of S is positive semi-definite and that the integral of M is just, it's the integral of the resolvent plus its Hermitian transpose, each of those integrals just gives the identity. And so you get that, indeed, the integral of u star M of S v is always less than or equal to 2. And that gives us the result. The final step of the proof was simply to relate the norm of f of a plus g of a star to the norm of f of a. So let this was just a few lines of algebra again. Let S be the sum, f of a plus g of a star. C omega, let that represent the soup over all analytic functions with norm 1, with infinity norm 1, the soup of norm h of a. Then just writing f star in the form s star minus g of a, multiply on the left by f of a star times f of a, and on the right by f of a. And we get these inequalities, and then finally we have this inequality involving C omega. Just solve that, and that's how you get the 1 plus the square root of 2. So it's really a very simple proof. Now, although that proof is very simple, it appears to be very hard to replace the 1 plus the square root of 2 by 2. And since I kind of like this problem, but I don't want to beat my head against the wall trying to prove something that seems to be hard, I decided instead to work on problems that are associated with this, not necessarily aiming to prove the conjecture, although I certainly wouldn't object to proving the conjecture. And one problem associated with this we call extremal Blaschke products. We had a Banff meeting with a few of the people from the AIM workshop. There's myself, Pamela Gorkin, Elias Begert, Felix Schweninger, Thomas Ransford, and Kelly Bickel, okay, in Banff. And what is an extremal Blaschke product? Well, the form of a function f, let me see if I can do this. The form of a function f that maximizes, I sometimes call this the Crouzet ratio. Michael takes the inverse of this so that he can minimize. But the form of a function f that maximizes this ratio, norm f of a divided by the maximum value of f on the numerical range, the form of such a function is known. It's of the form b composed with phi, where phi is any bijective conformal mapping from the numerical range to the unit disk, and b is a finite Blaschke product of degree at most n minus 1. So it's a function of this form. The alphas are less than 1 in magnitude, so all of the poles of this function are outside the unit disk. Functions of this form map the unit disk to itself. So for a given matrix A, and once we've set A and we've set the conformal mapping phi, we'd like to know, how to choose these alphas so that we maximize the norm of the quantity n1. And now, since we've taken B to be a Blaschke product, and B composed with phi then is a mapping from W of A to the unit disk, the denominator here is 1. So for a given A and conformal mapping phi, we refer to a Blaschke product B sub E, for which this is maximized, for which F sub E over equal to B sub E composed with phi maximizes this ratio. We call that an extremal Blaschke product. So these are, of course, important in studying Crouzet's conjecture, and we'd like to know as many properties of B sub E as we can. Probably the most important property actually appears in a paper by Crouzet, Gilfeather, and Holbrook from 2014. Suppose B sub E maximizes this Crouzet ratio over all Blaschke products B of degree at most k. Assume also that its norm F sub E of A is greater than 1. If it's 1, it's not not very interesting. Cruzet's conjecture for that matrix certainly holds in that case. Okay. Then the left and right singular vectors, u1 and v1, corresponding to the largest singular value of f sub e of a, are orthogonal to each other. That is, if v1 is a vector for which f sub e of a times v1 generates a vector whose norm is the norm of the matrix, and this, of course, is the spectral norm, the largest singular value, then the inner product of f sub e of a with v1 times v1 with v1 is 0. Okay, so that's one important property of extremal Blaschke products. What are some implications of that? Well, this implies that for most matrices, if you add the matrix, say a random matrix M to f sub e of a, okay, you will get a matrix with larger norm. Obviously not every matrix. If you add negative f sub e of a to f sub e of a, you will get a matrix with smaller norm. But for a lot of matrices, when you add them to f sub e of a, you will get something with larger norm. For example, you will get something for which f sub e of a plus m times the vector v1 has larger norm than f sub e of a. As long as the real part of the inner product of u1 with mv1 is greater than or equal to minus 1 over 2 sigma 1 times the norm of mv1 squared. What does that say? Well, that says that the only way that you could get something smaller in norm than f sub e of a would be if the something that you added had a negative component in the direction of u1, and that negative component was actually a pretty big fraction of the norm of the whole vector. Okay? In particular, if you add any multiple of the identity to f sub e of a, u1 star times a multiple of the identity times v1 is 0. So indeed, this condition would have to be satisfied, and you would get something larger. So when you have the optimal f and you add any multiple of the identity to it, you get something larger. Why is that of interest? Well, this is some results from Trevor Caldwell, Kinan Lee, and myself. Remember, Cruzet and Palencia showed that the norm of f of a plus g of a star was less than or equal to 2, where g of a was the Cauchy transform of f bar, and assuming norm f on w of a is less than or equal to 1. Well, if the boundary of w of a is a circle, then we can evaluate this integral in a nice way. It turns out that this integral is g of a star is just equal to the value of f at the center point of that circle times the identity. So by the previous argument, norm f sub e of a plus g sub e of a star has to be greater than or equal to norm f sub e of a, and now combine that with the Cruzet-Palencia result, and we've proved the Cruzet conjecture when w of a is a disk. Now that was already known. That was proved by totally different means, by Okubo and Ando in 1975, but this gives a nice way of proving that. Now we've done lots of numerical experiments with this. How do the numerical experiments work? Well, enter the matrix A. We use ChebFun. Use ChebFun to compute the numerical range, as Michael described, how it computes that, and also the conformal mapping from the numerical range to the unit disk. We then use an optimization code. I haven't been very sophisticated with this. I use fmincon in MATLAB to find roots alpha 1 through alpha n minus 1, constrained to have absolute value less than or equal to 1. Those would be the roots of the extremal Blaschke product for the matrix A and the conformal mapping phi. So we look for the roots that maximize norm B of phi of A. We try lots of different initial guesses for those roots, and then we accept the result for which norm B of phi of A is maximal, and check that all known properties, like this orthogonality of the largest left and right singular vectors, are satisfied. I see there is one question. Does someone have a question? I don't see it in the chat bar. Is there a question?
The name was question 4.
Question 4. I don't.
Your microphone is open.
Your microphone is open.
Okay, go ahead.
Okay, go ahead.
Okay. Okay. Yeah, but feel free to ask questions. Now, so I've run thousands of numerical experiments like this. In all numerical experiments that I have run, I've always found that norm f sub e of a plus g sub e of a star was greater than or equal to norm f sub e of a. So I will give that the name of my conjecture. And of course, if this could be approved, it would imply Crouzet's conjecture. But a proof still remains elusive. Another recent experiment I did, and I haven't done this on too many matrices yet, I wasn't really sure how it would turn out, was I wondered what would happen if we tried to maximize norm B of phi of A, subject to the constraint that it not satisfy the thing that I think the extremal B always satisfies. Namely, subject to the constraint that norm f of a plus g of a star be less than norm f of a. But of course, you have to allow it to be equal as well. And the interesting thing was that even with this problem, it always returns to me a solution where norm f of a plus g of a star is equal to norm f of a. I wasn't really expecting that. That suggests a sort of monotonicity. If norm f of a plus g of a star is less than norm f of a, you can probably choose a different f and make norm f of a larger, a different b and make norm b of phi of a larger. So that, I think, is perhaps more of an idea of how one might approach trying to prove what I believe to be true, that norm f of a plus g of a star, when we have the optimal f, is always greater than or equal to norm f of a. Are there questions at this point? Don't see any. Okay, then I guess the more we know about these extremal Blaschke products, the more likely we will be able to prove either my conjecture or Crouzet's conjecture. And so, as I mentioned, we had this meeting at Banff to see what properties of extremal Blaschke products we could derive. And these results are really due to Thomas Ransford. He noticed that we could extend this idea that the largest left and right singular vectors are orthogonal to each other in the following way. Let F sub E be extremal for the matrix A, and it doesn't have to be W of A. It could be another set, omega, but we're interested in W of A, the numerical range. Let V1 be a right singular vector corresponding to the largest singular value. And suppose we factor F in the form F1, F2. And there's a natural factorization when F is a Blaschke product of phi of A. You could just take some of the Blaschke factors to be F1 and some to be in F2. If we factor it as a product of functions, then we get these relations between the inner products. F sub E of A times V1 onto F2 of A V1 is sigma 1 squared times F1 of A V1 inner product with V1. And this generalizes the previous result, because if we take F1 to be F sub E and F2 to be F1, then this result just reduces to the previous one, that F sub E of A V1 inner product with V1 is sigma 1 squared times the same thing, which means that either sigma 1 is 1, okay? Remember, we had before to assume sigma 1 was not 1, was greater than 1. Or, in case it's greater than 1, that means F sub E of A V1 inner product with V1 is 0.
And there is a question.
And there is a question.
Yes. What is the application of such F to make the two sides equal? What is the, I don't understand the question. What is the application of F? Yeah, I don't understand. I mean, F and F plus G.
Miss Magalpur, your microphone is
Miss
open.
Magalpur, your microphone is open.
Ask your question.
Ask your question.
What is it?
To interrupt you.
Interrupt you.
Yeah.
Sorry.
It was for the previous slide.
It was for the previous slide, actually.
Sorry. And
Sorry. And
turn off your microphone.
Turn off your microphone.
Oh, yes.
Okay, thank you.
Okay.
Okay, go ahead. Mr.
Yeah,
Miss-
it was. Yeah, sure. It was for the previous slide, and I just confused that what is the application of this F to make equal the two sides. I mean, how it is important to find such an F. I missed this point.
Okay. And
Okay, I'm unmuted now. Yeah, so what I believe to be the case is that when we have the extremal F, it will always be the case that norm F of A plus G of A star is greater than or equal to norm F. So I said, okay, what if I don't necessarily go for the extremal F, but I go for the F that maximizes norm F of A, where F is of the form B composed with phi, subject to the constraint that this thing that I think always holds for the extremal one does not hold, okay? Then I will get an F for which norm F of A is less than the norm of the extremal F. But what I didn't necessarily expect was that it would always find one where norm F of A plus G of A star was as large as I would let it be in comparison to F. I let it be, I required it to be less than or equal to F, and it always found one where these were equal. which to me suggests some sort of monotonicity. Does that answer your question? Okay. All right, so I mentioned this generalization of the result that the largest left and right singular vectors of f sub e of a are orthogonal to each other, in that you can factor f sub e and get a relationship among the factors. Another interesting property of the extremal Blaschke product for a matrix A and a set omega, let V1 be a right singular vector corresponding to the largest singular value, then there exists a unique probability measure, mu, on the boundary of omega, such that for any analytic function h, if you look at the inner product of h of a V1 with V1, it's equal to the integral of h d mu. If further, I see some questions coming up, maybe. Okay, if further, sigma 1, the norm of f sub e of a, is greater than 1, remember in that case we said that the inner product of f sub e of a v1 with v1 would have to be 0, so that would, of course, would imply that this integral of f sub e times d mu is 0. And we can even say what this measure d mu is if phi is a bijective conformal mapping from omega to the unit disk d. Then this probability measure d mu is 1 over 2 pi times a function of phi of zeta, the absolute value of zeta prime, absolute value of d zeta. So that seems to give us some interesting information, additional information about the largest right singular vector of the extremal f. And I should also mention that someone brought up last time, what about the question of when you optimize not norm f sub e of a, but the numerical radius of f sub e of a. There are analogs of a number of these theorems when we call it a W extremal function and vector, because it's maximizing W of a, the numerical radius of a, rather than the norm. But there are analogs of these theorems for that. They're different, but I won't talk about those specifically. Oh, I also mentioned last time that when I've run numerical experiments looking for the Blaschke product that maximizes the numerical radius, I've often found that those are slower to converge. I really don't understand why. The optimization code works extremely well for finding the coefficient, the roots of a Blaschke product that maximize norm B of phi of a, but less well for finding roots of a Blaschke product that maximize the numerical radius of B of phi of a, and I don't know why. Okay, other questions about this extremal Blaschke product. Is it unique? We said it has to have degree at most n-1. One might expect that typically its degree would be n-1, but in fact that's not necessarily the case. Looking at an example, this example is due to Keenan Lee. He can answer these questions analytically. Consider the following 3x3 matrix with 1 and 1 minus t on the superdiagonal, where t is in the range from 0 to root 3 minus 1. The numerical range of this matrix is a disk about the origin of radius square root of 1 plus 1 minus t squared over 2. The natural conformal mapping to the unit disk would just be to multiply by 1 over r. So phi of A would be 1 over r times A. And you can show that that's similar to this Jordan block, which has norm 1, via a diagonal similarity transformation, namely this one. So it follows from von Neumann's inequality that the norm of B of phi of A will be less than or equal to the condition number of D, norm D times norm D inverse, times the norm of B of this matrix, which is a contraction, and therefore norm B of this matrix is less than or equal to 1. And so we have an upper bound on the extremal Blaschke product. Its norm must be less than or equal to this max of 1 over r and 1 minus t over r squared. Well, with a little bit of algebra, you can show that we obtain equality with the Blaschke product B of z equal to z. Oh gosh, this erases things. When t is in this range, between 0 and 1 minus root 3 over 3, whereas the optimal B for t in the range 1 minus root 3 over 3 up to root 3 minus 1 is B of z equals z squared. And you can plot the norm of this extremal B as long as t is less than 1 minus root 3 over 3. B of z is z, and its norm is given by this curve. After this crossover point, B of z is z squared, and it's unique once we cross that crossover point. That's the unique extremal Blaschke product, and the norm is given by this curve. So what this shows is that we don't necessarily expect the extremal Blaschke product to have degree n minus 1. Over this range, it has degree n minus 2, or 1 in this case. And there are points at which it is not unique. At this crossover point, both B of z equals z and B of z equals z squared, those are both extremal Blaschke products. Now, I've done lots of numerical experiments with random matrices. And of course, I can't be absolutely certain that I have B sub E, the extremal Blaschke product, but it satisfies all the conditions that I've mentioned, all the properties that I've mentioned. And I can't be absolutely sure what its degree is, because if it returns an alpha j, one of the roots equal with magnitude 1, that is just a scalar with modulus 1. It doesn't really contribute anything, and so that tells me, or suggests to me at least, that the degree of B sub E is not really n minus 1. Those roots aren't being used. And, well, interestingly, for 3 by 3 matrices, I guess it often gets an extremal Blaschke product of degree 2, but it also gets one of degree 1 fairly often. For 4 by 4 matrices, it was kind of unusual to have an extremal Blaschke product with that maximal degree 3. For 5 by 5 matrices, I think I found one case in 500 where the degree of the extremal Blaschke product was 4. It doesn't really show up on this scale, but by far the most common occurrence was that the degree is less than n minus 1. And for larger matrices, this holds as well. For a 6 by 6 matrix, in 1,000 cases, I didn't find any where the degree of the extremal Blaschke product was 5. In fact, it often, the most popular degree seems to be 2, which, I don't know, suggests that maybe we could actually figure out what the extremal Blaschke product is for some matrices. Okay, but those are the numerical experiments. Okay, are there questions on any of this? I don't see any. So I will move to another related topic. I see somebody's typing. No. Okay. So I will move to another related topic. Other K-spectral sets. So I mentioned that the Crouzet-Palencia theorem about the numerical range being a 1 plus root 2 spectral set for A was pretty simple. One might ask, well, can we apply similar ideas to other sets and establish that some other sets in the complex plane have the property that norm f of A is less than or equal to some small number times the maximum value of f on that set. If that number is k, it's called a k-spectral set. Well, again, Caldwell and Lee and I did some work on this. And what we did was we basically just copied the work of Crouzet and Palencia, but we didn't assume that our region contained the numerical range. We only need to assume that it contains the spectrum so that f of A is well defined. And we looked at what? This keeps erasing on my screen. I'm not sure if it does on yours, but we looked at the matrix S equal to f of A plus g of A star, but now we added something in to account for the fact that on the boundary of our region omega, the smallest eigenvalue of this matrix M of S, which was like the resolvent plus its Hermitian transpose, that might be negative. And we could also take advantage of the fact that it was positive, which if we're outside the numerical range, which Crouzet and Palencia did not do. Okay, they just said, well, it's greater than or equal to 0 and went from there. And we showed that the norm of this matrix is sort of like f of A plus g of A star was less than or equal to 2 plus an expression involving this smallest eigenvalue. So if we could find some sets where we could get bounds on the smallest eigenvalue of this resolvent plus its Hermitian transpose, then we could establish some results about other K-spectral sets. And in work with Michel Crouzet, we came up with some things. He came up with some things, really. Oh, and by the way, the proof, as I mentioned, for this problem is essentially like that in the Crouzet-Palencia paper. So working with Michel Crouzet, he came up with some interesting sets that are also K-spectral sets for A. So first, suppose that capital R is the max of norm A and norm A inverse. Look at the annulus consisting of an outer radius equal to capital R and inner radius equal to 1 over R. That set can be shown to be a 1 plus root 2 spectral set for A. You do that by determining those integrals I had before involving lambda min, using the fact that lambda min on the outer circle is positive, on the inner circle it's negative, but the positives and negatives cancel each other out enough so that we can show that this annulus is a 1 plus root 2 spectral set for A. More generally, assume that the norm of A minus omega 1I is less than or equal to R1. So in this picture, omega 1 would be 0, R1 would be capital R. And the norm of A minus omega 2I inverse is less than or equal to R2. So in this picture, take omega 2 to be minus 2 and R2 to be little r. Then the set consisting of the inside of this disk and the outside of this one, that is also a 1 plus root 2 spectral set for A. And again, the idea is to figure out what lambda min looks like on both of these disks and to cancel negative values with positive values as much as possible. More generally, if we take omega to be the numerical range without a disk about some point little omega with radius 1 over the numerical radius, now we're switching from norms to numerical radius of A minus omega I inverse, where this disk is either inside W of A or on its boundary intersects W of A in a finite number of points, then this set, we couldn't get 1 plus root 2, but it's the 3 plus 2 root 3 spectral set for A. So it could be an annular-like structure, like this one. And of course, all of the eigenvalues have to lie in this set omega. It takes a little bit of checking to make sure, but they do. It could be a cutout region where we take W of A minus this disk. Or the disk could even intersect the numerical range in 4 points, and then we would have 2 separate regions. And together, these 2 separate regions would be a 3 plus 2 root 3 spectral set for A. Okay, well, that's the theoretical results that have been developed recently. I now want to just mention a few applications. If there are questions, I can pause for questions. How you show when omega equals W of A, then delta equals 0. Well, it's kind of complicated. Oh, wait a minute. That one. Okay. When omega is W of A, lambda min of this matrix is 0. That's why delta and gamma are both 0 when omega is W of A. Okay, other questions? All right, well, let me just mention a few applications of this. Somebody asked last time if it really makes a difference application-wise whether we have, excuse me, 2 or 1 plus the square root of 2. As far as I know, the answer is no. But from a mathematical point of view, 2 seems so much more natural. So I won't try to pretend that 1 plus the square root of 2 makes a big difference in applications. But anyway, maybe there's one where it does. I don't know such applications. So Michael Overton mentioned applying this to the GM-Res algorithm for solving AX equals B. The GM-Res algorithm generates an approximate solution, xk, for which the residual, rk, is minimal. Take all kth degree polynomials with value 1 at the origin, okay, and minimize norm p of a times r0. And that's less than or equal to what we get if we minimize norm p of a over such kth degree polynomials with value 1 at the origin. If 0 is not in the numerical range, then from Crouzet and Palencia, we know that norm rk over norm r0 is less than or equal to 1 plus root 2 times an approximation problem on the numerical range. How small can you take a kth degree polynomial with value 1 at the origin, try to make it small on the numerical range, that how small you can make it, that gives you an upper bound on the residual in GM-res. But of course, this estimate is not useful if 0 is in the numerical range. So we can use some of these other sets. And this is an example that has been used way too often, but I'll use it one more time. It's a matrix due to Joe Gerther. Its eigenvalues are the blue x's. The black line, which I can't trace too well, this one is the boundary of the numerical range. Here is a disk about the origin whose radius is the numerical radius of A inverse. So according to the theorem of Crouzet and me, this black set, that's the exterior of this disk with the interior of the numerical range, that intersection, that is a 3 plus 2 root 3 spectral set, because I took the radius of that disk to be the numerical radius of A inverse. So we get a 3 plus 2 root 3 spectral set for A. The red curve was shown by different means, which Michael Obert had mentioned, to also be a 1 plus root 2 spectral set for A. Now, probably a more interesting application would be to rational Krylov methods for approximating f of A times B. Well, a rational Krylov method generates an approximation, I'll call it R sub m of A times B, to f of A times B, where R sub m is a ratio of polynomials, and the denominator is fixed. The Q sub m minus 1 is fixed. You probably want the poles of the rational function to match those of f, if f has poles. Okay? So a rational Krylov space of order m is just Qm minus 1 of A inverse times something from the ordinary Krylov space. The rational Arnoldi algorithm for approximating f of A times B chooses its approximation, well, if Vm is an orthonormal basis for this rational Krylov space, it chooses its approximation to be Vm f of Am Vm star times B, where Am is the compressed matrix Vm star A Vm. And well, this has a near optimality property, which can be derived very easily from the observation that if f of A times B actually lies in the Krylov space, in the rational Krylov space, then this generates the rational Arnoldi approximation is actually equal to f of A times B. Therefore, the difference between f of A and times B and its rational Arnoldi approximation can be written as the difference between f of A times B and any function in the Krylov space plus the approximation to that rational function in the Krylov space, which is the same as the rational function, minus the difference between that and the rational Arnoldi approximation to f. So using the triangle inequality, we find that the difference between f of A, B, and its rational Arnoldi approximation is bounded by the difference between f of A and any rational function of the form Pm minus 1 over Qn minus 1, and the difference between f at this compressed matrix A sub m, and likewise the rational function applied to A sub m. Since W of A sub m, the numerical range of A sub m, is a subset of the numerical range of A, it follows from Crouzet-Palencia that we can bound the difference between the true f of a b and the rational Arnoldi approximation by, now we get a factor of 2 because we have these two terms here. 2 times 1 plus root 2 times how well you can approximate f on the numerical range using something of the form Pm minus 1 over Qm minus 1. So just to illustrate this, so that's the let me go back. That's from the Crouzet-Palencia result. But of course, if there's a pole of f in the numerical range, that's not very useful. Okay, we can't approximate f well in that region if it has a pole there. If f has a pole in W of a, we want R sub m to have one at the same point. For example, if the function we're trying to evaluate is f of a equals I minus e to the a inverse. So that function has a pole at 0. So we can't make the difference between f and a rational function approximation tiny where there's a pole, or especially close to where there's a pole. But if we can make it tiny on, well, this red set that I've pictured for the Gercher matrix, or this red set that I've pictured for another matrix called the smoke matrix. This is actually an annulus. The inner dimension, the inner radius is very small, but it's there because I don't want to get too close to 0. If we instead try to approximate f with a rational function on these sets that are bounded away from the poles, then we can do quite well. So the red curve in each plot is the boundary of the intersection of W of a with the disk about 0 of radius 1 over the numerical radius of A inverse. So those are 3 plus 2 root 3 spectral sets for A. Okay, that is pretty much what I had to say. There's one more picture. I just wanted to remember my trip to Iran in 2011, I believe. And I'm hoping that one day we will be able to visit each other's countries again. In the meantime, I think this virtual meeting was a great idea, and I thank the organizers and would like to ask for any questions.
Thank you very much.
Thank you very much.
Is there any questions or comments?
Is there any questions or comments?
Hello, can you hear me?
Hello, can you hear me?
Yes.
I am.
I am.
Maybe turn off your mic for a second so we don't get the echo. Well, great talk as always. Thank you very much. You said that you referred again to this business that you get slower convergence when you optimize the numerical radius ratio instead of the standard one. You get slower convergence. I was wondering if that is because for the numerical radius variant, it seems you have to let the degree of the polynomial go to infinity, whereas with the Crouzet ratio that I talked about yesterday, you don't.
Of course, with Blaschke products, the one that optimizes the numerical radius still has degree n minus 1 at most.
Yes.
Yes.
So I don't know why the optimization code is slower.
Mhm.
Okay, thanks.
Okay, thanks.
All right. Chi-Kwang Lee says Crouzet for joint numerical range is a very good question. I have no idea. Let's see. Is there similar Crouzet's conjecture for joint numerical range? Oh. In your opinion, what can be I have no idea. good research problem.
Professor Clifton, you can talk.
Professor Clifton, you can talk.
Can we determine for which x in Cn and corresponding z equal x star a x takes its maximum? No, I don't know how to determine that other than numerically. I mean, I compute the extremal Blaschke product and then compute its singular value decomposition. I have no idea what x would be, what that largest singular vector would be a priori. Is that what you were asking? Oh, how was the result about Krylov methods affected by the condition number? As Michael mentioned last time, one is tempted to analyze the GM-Res algorithm in terms of eigenvalues, okay? Or the condition number would really be the ratio of the largest to the smallest singular value. But unless you know something about the eigenvectors, you really can't say anything about the convergence rate of GM-Res based only on eigenvalues. But if the eigenvectors are well conditioned, then all of this is sort of moot. You should analyze it in terms of an approximation problem on the eigenvalues of the matrix. Let's see. You use singular value vector. I use the singular vector, right and left singular vectors associated with the largest singular value.
Okay.
Okay.
If there is no
If there is
questions,
no questions,
thanks again,
thanks again,
Professor
Professor
Greenbaum.
Greenbaum.
Very wonderful
Very
talk.
wonderful talk.
Oh,